Greetings from Purdue University and welcome to the NanoHub course Atoms to Materials. I'm Alex Strachan. We all know that materials are intricately related with human development, from prehistoric times, where we name periods after the dominant materials, to an aluminum alloy that enabled the Wright brothers to design an engine light enough for the first propelled flight in 1903. Over 100 years later, advanced materials today enabled efficient airframes, new cathode and anode materials opened the door to electric vehicles, and at the smallest of scales, our cell phones and laptops have billions of transistors that have key materials that are only a few layers of atoms in thickness. Perhaps surprisingly to some, material science plays a key role in the design and manufacture of drugs and help athletes break world records. In the course, we will look at these key materials at atomic scales. We'll learn how they look and how they work at those scales. As material scientists, we use this information to design even better materials. In Atoms to Materials, you will learn the fundamental physics that govern materials' behavior at atomic and molecular scales. Now, these equations are very difficult to solve and can only be solved analytically for few and simple examples. So in the course, we'll use powerful simulation tools, research-grade simulation tools, to explore more interesting examples and make predictions of properties. All the simulations will run using NanoHub's cloud computing resources, so you don't need to worry about installing software or even have access to computing resources. We will learn that to describe materials at atomic scales, we need classical and quantum mechanics. We will also need statistical mechanics to relate the microscopic world to thermodynamics and macroscopic properties. To a large degree, these physics were known by the late 1920s with the final formulation of quantum mechanics. However, as we said, the equations are very difficult to solve. With the advent of computers, our community advanced the theories further and developed algorithms that enable predictive material science. In the course, you will learn about density functional theory calculations and molecular dynamics simulations. To finish, the physics and tools that we'll learn in the course are attracting growing interest from industry and academia, as we think they can be used together with experiments to reduce the time and cost involved in the discovery and deployment of new materials that can benefit society. I invite you to join Atoms to Materials, and I look forward to seeing you all in the course. Thank you very much.